Ladies and gentlemen, so today I'm honored to introduce our special guest in today's conference. So Pradeep Sindhu. And Pradeep is the co-founder and the CEO of Fungible Network, and a Silicon Valley startup aiming to revolutionize the performance, reliability, and economics in data center. And more importantly, he is the founder of Juniper Networks. Which is a company that is well known to us, but and it has a brief introduction. Like the company is recognized for inventing silicon-based router, a key innovation that advanced internet age. So today, Pradeep will give his vision about the next generation of infrastructure technology. So let's give us the warmest welcome again.
Thank you, Hong Chen, for that welcome. So this morning, good morning, everyone. This morning, I want to talk about why the industry needs a true data center fabric. There's a lot of things that Dennis Sky mentioned in his talk, which I agree with wholeheartedly. Probably the most important of them is that for cloud data centers, scale is the single most important thing. This was true for the internet as well. Scale was number one. And with scale comes the requirement for reliability, for operational simplicity, and all those things. But today I want to focus on the network inside a data center. And in particular, why the industry today needs what we are calling at Fungible a true data center fabric. That's what the talk is about. I think to begin with, it's important to set the stage on some fundamental industry trends that we see. And these industry trends were the foundation of Fungible. Number one is that we're seeing that Moore's law is going to plateau, is plateauing. In fact, possibly the last CMOS technology is going to be 5 nanometers. 7 is already here, 5 is next. And you can see that compute actually plateaued first, network is next, and then storage is going to be right behind that. And so by about 2021, we don't expect that we're going to get any more gains from CMOS silicon technology. This is really fundamental and deserves a response. The second trend is that hyperconnectivity, which is the desire to connect everything to everything else, is absolutely in play. It's the basis for the internet, but it's happening everywhere. Because this is the way to deliver value. The third trend, which is relatively new, it's only a decade old, which is that applications are becoming more and more data-centric. And applications have become more and more data-centric because people have discovered that instead of having a small amount of data and writing clever and large programs, if I have a lot of data and I can actually examine this data and process it quickly, I can actually get insights. Maybe I can get insights about how to operate a data center. Maybe I can get insights about how my customers behave. And these insights can be turned into money. And this is why everybody is trying to collect lots and lots of data. The fourth trend, of course, is that with the concentration of computing and storage into large-scale data centers, these large-scale data centers become very, very juicy targets. And this is a problem. And so security threats are continuing to accelerate. Now, I may point out that in this chart, you can see that from 1989 to 2019, the ratio of I/O to compute has gone up by some 600 times. Back in 1989, CPUs were running at 50 megahertz, networks were at 3 megabits per second. Today, networks are at 100 gigabits per second, CPU speed is about 3.3 gigahertz. So you can do the computation, it's almost 600 times. When a number that fundamental changes by over 2 orders of magnitude, something is going to break. Okay? This is why we say that we are now going from a compute-centric world to a data-centric world. Towards the end of the compute-centric world, we had scale-out homogeneous architectures. We believe that the next architectures are scale-out heterogeneous. I think Dennis also mentioned this in his talk. And you can see this already, that the engines that are there in the data center, CPU, GPU, TPU, FPGAs. And we think one very more important element called the DPU, which is missing. And that's something that I will talk about as well. Now, the data center architecture faces a fundamental problem today. The fundamental problem is this, that modern applications are data-centric, but the architecture of the servers inside the data center is vehemently compute-centric. It was designed some 35 to 40 years ago. The architecture of the computer, the division of labor between software and hardware was done 35 to 40 years ago. Yes, that computer architecture has improved in performance dramatically over the last 35 years. However, this architecture progressively is facing a problem, and this is the transformation that has to be made. So I've used the term data-centric many, many times, and other people have used it also. I want to now define it precisely. This is important. For us, data-centric means something very specific. There are 4 elements. All of them have to be there. Number one, that the workload arrives as packets over a packet-switched network. Number one. Number two, these packets are coming from many, many, many sources, not just one source. So there's a lot of context switching which is going on. Number three, the computation itself is stateful, not stateless. And stateful computation just means that the processing of a single packet actually can only be done if the previous packets have been processed. Routers and switches are stateless. They're not stateful. Okay? And finally, that I/O dominates arithmetic and logic. This is the new thing. When you combine all 4 of these attributes, that workload is called data-centric. And we believe that in data centers today, data-centric workloads are probably a third of where the energy is spent, maybe more. Now, to give you specific examples of data-centric workloads, the network data path inside a server, the storage data path, the security data path, the virtualization data path, load balancing, IPsec, TLS, all of these are examples of data-centric workloads. Now, when you look across the elements, the fundamental silicon elements that are used to build data centers, these are general purpose x86 CPUs, network interface cards, switches, routers, load balancers. There is a fundamental set of capabilities, 2 capabilities that are missing from those silicon elements. One of them is the ability to efficiently process data-centric workloads. Okay? That's number one. Number two is the ability to interconnect many, many hundreds of thousands of heterogeneous servers together into a single computing facility. Those 2 elements must be combined into a single piece of silicon. And what Fungible is doing for the industry is it has defined and developed the concept of a new kind of microprocessor called the DPU, which combines these two capabilities into a single device in such a way that that device is fully programmable. So I repeat, this device is fully programmable, yet it provides those two capabilities in one piece of silicon. Now, the second capability we call TRUEFABRIC. And the first capability, of course, provides at least an order of magnitude more efficient operation for data-centric workloads than x86. Now, our vision for the data center architecture is actually simple. If you try to build things which are very complicated and you try to build them at scale, you will not succeed. I think if there was one thread that ran through the discussions this morning, it was exactly that. It is simple, scalable, controllable elements. And we 100% agree with this vision. And in fact, to show you what the culmination of that vision is, we believe that in the future, data centers can be built using 4, maybe 5 kinds of servers. Not 100 different kinds, just 4 or 5. Well, what are these servers? Number one is a 1RU general purpose x86 server with its DRAM and 1 DPU, which connects it to the network. The second is an AI server, or AI plus analytics server, which has 4 GPUs and 1 DPU, connecting it to the network. The third one is an SSD storage server, which has a bunch of SSDs and a DPU connecting it to the network. And the last one is a hard drive storage server, which has a DPU connecting it to the network. Now, invariably, this list of 4 will grow over time because we know that in terms of storage, you're going to end up with 2, 3, maybe 4 tiers of storage. But unlike previous storage solutions, all these tiers will be directly connected to the fabric. So now, all of these resources, general purpose computing, AI computing, SSD storage, hard drive storage, they will be fully disaggregated and pooled across the entire data center at scales which are somewhere between the maximum scale we believe will be somewhere around 10,000 racks in a single building. That is possible. Okay? Not only is it possible, it is feasible today. And the overall bandwidth of such a network, a fabric that connects it, we can see doing a single fabric which is somewhere between 10 petabits per second and 20 petabits per second in a single building. This is clearly possible today. Okay? Now, when you look at the picture on the right, the thing which is really important to say, that when you have a small number of server types, where hundreds of thousands of these servers are connected by a single network fabric, the computational horsepower of such a data center depends very strongly on the capabilities of the network that interconnects these servers to each other. This lesson is easy to see when you look at the evolution of the internet. When the internet was slow and incapable, you did not have many applications. As the internet became faster and faster and more capable, the world has been stunned at what can be done. The same thing is playing out inside data centers today. Exactly the same thing. And for me, I've seen the internet era play out, and I'm seeing now this thing play out in the middle of data centers. And it's actually remarkable to see the same phenomenon happening at smaller scale, but the essentials are the same. Now, what is a true fabric? It's very interesting when a term like fabric comes out, and the term fabric was first used at Juniper when we defined a term called QFabric. What was interesting to me is within 3 months, every company, every networking company had a fabric. Independently of whether they had it or not, they had a fabric. Okay? At Fungible, we are not a marketing company, we're a technology company. So this time, I'm going to define the term true fabric very clearly. You're all technologists. Number one, true fabric is packet switched based on open standards, particularly IP over Ethernet. Not InfiniBand, not fiber channel, IP over Ethernet. Number two, the bandwidth with which one of those 4 servers is connected to the network is independent of the scale at which I want to build this fabric. Extremely important. This is actually the definition of scalability. Number 3, we would like full cross-sectional bandwidth, any to any, from any server to any other server, with no constraints at all. I don't want the application writer to know that, oh, I can go from here to here, but not from there to there. Because the moment you make those constraints, your application becomes impossibly hard to write at scale. This is the reason why you want full cross-sectional bandwidth with no constraints. Number 4, I want end-to-end congestion control and error control. This is the single thing that the industry has not been able to solve, except using TCP/IP. The 5th thing, which Dennis also mentioned in his talk, is low latency, zero load latency, plus excellent tail latency. Yeah? Scalability from tens to hundreds of thousands of servers in a single data center. You also want incremental expandability with no downtime, because as you add capacity, you want to be able to do it without turning off the existing servers. These are fundamental requirements. Given the problems we are having with security, you would also like end-to-end encryption for high security. You want the ability, even though the hardware topology is fixed and very much like a class-based any-to-any network, you want the software-defined connection topologies to be flexible and dynamic. And then finally, you want this network fabric, this true fabric, to support in an efficient way many, many different kinds of protocols. Byte stream protocols. TCP is a byte stream protocol. RDMA is a byte stream protocol. Messaging protocols like RPC, NVMe over Fabric, as well as things like unicast and multicast. These should be supportable efficiently. Well, that's true fabric. Now, I will make a prediction that within 6 months, many people will claim to have a true fabric. I don't think they will actually have a true fabric. Now, if there's one thing you want to take from my talk this morning, it is this statement. So I will read it carefully. The utility of an interconnection network, any network, it is maximized when that network is scalable, when it is efficient, meaning you can run it close to 100%, it's reliable, the communication is interactive, back and forth, not just bandwidth, but latency, secure, and fully connected in a way that does not limit the modes of communication. That's it. This is very important and fundamental. And I think Dennis mentioned again in his talk that this is fundamental. Now, given the fact this is important and fundamental, you should not be surprised that many, many, many people have tried to solve this problem before. It's a hard problem. Well, let me give you some examples. Data center Ethernet was an early attempt. The problem was limited scale, congestion. It didn't handle the problem properly. There was DC-TCP. I think this was invented by Google. And Google did just about as good a job as you could in software. Okay? TCP is a wonderful protocol, but it was designed for long distance communication, and it does a pretty darn good job of congestion control over the wide area. In fact, nobody knows how to do it better. Fiber channel. Fiber channel does hop-by-hop congestion control. It also has limited scale and has what's called head-of-line blocking. It is also deadlock prone, and it separates the network out for storage from compute. Not a good idea. Same thing with, well, FCOE tried to do that on top of Ethernet, but it has the same problems. RDMA, particularly RDMA over, which is a Rocky V2 version of RDMA, suffers from the same hop-by-hop congestion control regime. And it too is deadlock prone. It's also byte stream based. And we think that instead of basing everything on byte streams, the fundamental underlying layer needs to be message based, like UDP. Okay? You need to provide these capabilities in a message based, because you can implement byte streams on top of messages. Doing messages on top of byte streams imposes additional work which is unnecessary. Okay? Now, Fungible has defined a fabric control protocol that we call FCP, which actually implements TrueFabric today. And we are working together with Alibaba to demonstrate the capabilities of FCP. This protocol is built directly on top of IP-UDP, and it's fully open standards compliant. In other words, any switch that exists today, this protocol can run on top. The server bandwidth is independent of data center scale, up to 13 to 15 petabits per second. Full cross-sectional bandwidth with no constraints. We provide end-to-end congestion control at very fine grain, at the granularity of 5 tuples, with fairness across the entire network. This is a breakthrough. For small deployments of 128 racks, we achieve 4 microseconds, 4.5 microseconds of one-way latency. And for very large deployments of 4 to 10,000 racks, about 10 microseconds, zero load latency. And the latency jitter is about 25% of the zero load latency. So these are very, very good numbers for anyone who is familiar with networking. We also do built-in security via encryption end-to-end. And a network can be logically partitioned, because what FCP does is it sets up virtual tunnels from any endpoint to any other endpoint. And it exploits all the possible physical paths that are there in the network. Now, you might ask, well, what's the overhead of the protocol? What does it impose? Well, for most traffic types, the overhead is less than 4% in terms of the total amount of additional information. What is also very important, and I think this was stressed in multiple talks this morning, reliability and visibility. What FCP does is it permits you to detect failures independently of what the source of failures are in the network in less than 50 microseconds. 50 microseconds, not milliseconds, microseconds. And to recover from that failure in less than 1 millisecond. The reason you can do this is because the latencies inside a data center are not tens of milliseconds. They can be down to tens of microseconds, max. Okay? Now, TrueFabric has some very interesting benefits. The direct TCO benefits of using a DPU and a TrueFabric is roughly 3 times compared to a network that does not have this element that we call a DPU. And that 3x improvement comes from improving the network, offloading the CPU by about 2x, and then making use of erasure coding and compression pervasively on all your storage, not just your cold storage, but your hot storage as well. So, of course, if today you are already using these techniques, you're not going to see a 3x improvement, maybe you'll see a 2x improvement. Yeah? But these improvements are there nonetheless. Having a TrueFabric will have resource pooling benefits. And let me give you an example of what kind of benefit you might get. Take a single rack, which has 36 servers, and each server has 8 terabytes of SSD storage. Well, if you can pool that storage across all these servers, you can see approximately a square root of n improvement. So whenever you have n resource pools of 1 unit, and you pool it together into a single pool of n units, actually Peter Denning, in his PhD thesis on paging, proved that the benefit is roughly on the order of square root of n. You can go back and look at his thesis. This was many, many years ago, 40, 45 years ago. But that result still stands because it's a mathematical result. Well, you can see that the benefit is equivalent to square root of 36, which is 6x. This is not a small number, right? Now, we don't want to claim that if you do this across the entire data center, you'll get, 100x improvement. No, because there's a law of diminishing returns. But nonetheless, the numbers are large. TrueFabric also has a latency benefit, which is phenomenal. And the latency benefit derives from the fact that the tail latency is very good. Well, when you have a user which is coming in over the wide area, that one request from the user normally turns into hundreds of microservices requests over the internal network. If your tail latency is bad, the user is going to be dissatisfied. With a tight tail latency, you can actually get very, very good service. And if you get very good service, users will not be frustrated, they'll be attracted to your network. Okay? So this is what the tail latency for a TrueFabric looks like in orange. And the traditional ECMP-based networks, the tail latency looks like the blue. Okay? There's also a huge simplicity benefit. Today, I believe that every large-scale data center builder has dozens of different server types. And you're forced to do that because those servers are hyperconverged. Once you disaggregate your resources into 4, maybe 5 or 6 server types, the design of these servers is much simpler. It's much more uniform, fewer variants, uniform architecture. They're simpler to cool. In fact, what this goes to say is that once you have a high-performance TrueFabric, you can use it to get a simpler, more uniform architecture, which is easier to manage. There's a huge reliability benefit to TrueFabric also. The topology I've shown here is actually a topology which is doable at very large scale, actually a scale of all the way to 9,000 racks. Now, in order to do that, you have to use large-scale boxes, which you may or may not like. But if you want to use single-chip solutions, you'll have to add one more layer. But despite that, the point being that the spines in this architecture are independent of each other. And effectively, this architecture gives you 1-for-n redundancy. So individual spines, individual links, they can all fail. All that will happen is that you'll recover in less than 1 millisecond, and you lose some of the bandwidth of that TrueFabric. Security benefits. I mentioned that all the bandwidth inside a data center, DPU to DPU traffic, is fully encrypted. Traffic which is at rest inside storage is also always encrypted by default. Today, it's not possible to do this because it's too expensive. Well, once everything is encrypted, it's actually much more difficult for somebody to come in and steal information. This is very important. Okay? Finally, the conclusion is that the infrastructure for data centers, which is particularly the compute servers and the storage servers, their design needs to go from being compute-centric, which simply means that an x86 is sitting in the middle of the universe, to a design which is data-centric, where data can be moved very quickly and efficiently, and that requires, it demands the existence of something we call a true fabric. So we believe that TrueFabric is a fundamental enabler for this transition. We are committed to making TrueFabric an open standard, working together with companies like yourselves and the ITF to open it so that this fundamental technology is used pervasively. Thank you very much.
This talk is very inspiring, and I'm sure that after this talk, everybody will remember one word, which is true fabric, which is so true. Okay, let's thank Pradeep again.